Hello, in this tutorial I want to introduce the concept of groups and how these groups relate roughly to ParaView's concept of blocks and how those can be related to material properties that we want to set for our finite element models. So first thing I'm going to do is to load a simple kind of dummy model which is just been created to test a couple of features, and this can be found in this grouping model directory just called block. And the first thing I'm going to do is actually it contains some lumps of stuff around the model which is just meant to be noise, but just to demonstrate that I'm going to click this checkbox to say that to keep the components, so that the plugin is actually going to go through. It's going to do an image processing technique called connected components, and it's actually a 3D image block model. Oops. But in this particular case, because we've asked it to keep those components, it will keep them and label them separately. So the actual object of interest is in here, and it's got some different materials defined in it. But because this is just the connected components image, which if I show the color legend, you'll see that they're labeled sort of from 1 to 6, from size, kind of decreasing size along upwards, as it were. So it's not a very interesting model, this, but it does interest, allowing me to demonstrate one other feature, which is if we open another window in ParaView, we can use the spreadsheet to actually look at our model. And if this were a model with a number of disconnected components, such as a jawbone or some other bone that was disconnected in some way from the main element, then we might be interested in setting vectors to point from one thing to another, or forces. So if I wanted to know maybe what this sort of target point here was, I could use the spreadsheet function and this particular button called show only selected elements to actually query that point. And then, because our finite element solver can't cope with more than one object, we'd have to write this down. We can get rid of the window now, and I want to run this again without doing the connected components thing, or rather it's running the connected components, but it's now going to get rid of all the other objects in it apart from the first and largest one. So if I run this again, I can get rid of the color bar now. What I'm actually seeing is how everything else has been removed. This is the single largest object in the scene, which it thinks is the one that we want. And if I flip over now to the group file, the original group file looks like this, and you can see what we actually did is we told the plugin to load a 3D image, which is this, and we asked it to form 3 groups using labels 1 to 99, 100 to 150, and so on, with these names. This fourth flag here is about whether we allow this material to remodel, which is something we'll come on to a bit later in another tutorial. So we defined 3 groups, but in actual fact ParaView noticed that there was an extra label in there that wasn't defined in a group, so it gave it its own group, and that is the policy with our plugin. If you said groups was 0, it would take every label that it found and give it its own group, and then each group can be defined around different materials. So if I just go back again and look at the materials file that was created, we should see that that those four materials that we can see in this object are related to particular material properties by those groups. So labeled 35 is related by the first group, and that first group was bone, which, if you remember, was labels 1 to 99, and it's going to have these material properties. So that is basically how material types and groups are matched in VOX-FE. One other thing to take note of, though, is that we might want to place boundary conditions on our object, and we might want to be able to remove these sort of surrounding materials to actually do that. So what we can use is, we're using the concept here in ParaView of multi-block, so we can use the extract block function, but we've placed this within a button in the VOX-FE toolbar anyway, because the ordinary function needs a couple of parameters setting to work properly. So if I go ahead and click that, and then it gives us the option of choosing from particular blocks, as ParaView calls it, and then in that way it means that we can choose points around the surface, points that we previously couldn't see, and we can even narrow it down a little further. Or we can look at the others parts and maybe place points of interest or examine what's going off inside this object a lot more clearly. And I think 195 was a sort of stray object. I mean, maybe we knew about that all along, so it wasn't a problem, and we knew the plugin would find it. Or maybe we didn't. It's quite easy to miss certain labels, and this is a very good check to actually have a look to see whether the groups marry up to the labels once you've got the model imported. And this gets a bit more interesting, I think, if we move on to a more realistic model. So if I'll delete these objects and go to an intensity mapping example, which we have in this third directory. So in this directory I've got the phantom data that was actually scanned with the bone, and I'm going to try and load the bone at the moment, which is some horse trabecular data. And there's our group file for this, which I'll show you in a moment, because it takes a minute to load. And we have to set some parameters anyway, so I've worked out these parameters in advance. We're going to want to use intensity mapping for a 2D image series. I have in that directory just 0 to 20 as slices as an example. We're going to give the main range. It's always usually going to be bone that we're interested in giving this sort of range of moduli to. And I've worked out roughly in advance that in our image this equates to about 115 to 180 in terms of image intensity. This is using Carter and Hayes equation coefficients. If you have a look in the guide document, explains that a bit more clearly. And by using samples across that phantom data, which I'll show you in a second, and taking quite a few measurements and taking averages and doing a regression, I worked out that this is actually, these two boxes specify a mapping between the grey level intensity and the density. So I worked out that it maps from a grey level intensity 103 to 1.2021, which is one of our standard samples, and 136 to 1.9033. Poisson's ratio very often going to stay the same. We ask the system to create an approximate number of divisions based on what we're actually asking across this range, and what's actually present. The VOX-FE tries to make a decision, but basically it's going to try and keep to whole integer kind of divisions, because only integers make sense in terms of image intensities, or at least in our images. So I'm going to create some other materials as well, even though there aren't really any other materials, it's just for illustration. So if I create let's say 101 to 114 and call that marrow, and I'll give this a very low modulus, and just for illustration, you don't have to give these materials particularly in order, but if you overlap them, things might go wrong. And I'm going to say, let's say 80 to 100. I'm just going to call it air, and I'll give this you have to give it some kind of real modulus, or else things will probably be ignored. So I'm going to just give it a very low modulus, and then I'm going to give another material, let's say above 180, so let's say 181 to 1000. Let's give it a name, metal, and let's give it a fairly high modulus in this case, and that will do to illustrate the principles of what's going on here. So if I'll click apply, it'll take a minute to load, so I'll go over and show you what some of these images actually look like. So if we go into phantom data here, have a look with this image viewer, that's what the phantom data, these samples of known density, we're using to calibrate the scan. So this was actually scanned along with the horse trabecular data, and you can see that, I mean, there are kind of slight variations in what's happening with the density here, so it's a good idea to kind of take averages, and I took 5 samples or something from each sample from about 6 slices, I think, and prepared a regression line. The actual bone data itself looks like this. So it's just trabecular data in this case. I think in some ways this would be more sensible to apply over data that actually included cortical bone and trabecular bone, because there you can actually see differences in the apparent density, and you would want to reflect those in the kind of elastic moduli that you are wanting to model. And you can also see that there are artifacts and there's some noise in here. What we're actually asking VOX-FE to do here is to kind of threshold about certain key values, and that's always fraught with a choice of which is the best threshold, even if there is one. So in places the trabeculae get very thin, it's going to mix in with the background. So the other thing to just notice here is how the original group file looks, because in actual fact what we've done is we're saying load all these TIFF files, we gave it a voxel size, and we didn't define any groups. What we're actually asking VOX-FE to do is to choose our groups for us and to map them to the range of the bone that you told it was present. So from 115 to 180 or whatever, it decides how many intervals to choose, and then it will set groups and relate that to the material properties later. So I think it must have finished by now, so I'll go back to the image in ParaView, and this actually demonstrates one very cool thing about ParaView. It's using a sort of level of detail operator here to reduce the resolution as we're trying to move the object around, and then it renders it more fully when you stop clicking. And it has it's imported our dataset in it, and it's decided that the 4 groups that we suggested are here. And if I go ahead and extract blocks, then it means that we can choose our bone layer and apply. I think it's choosing some slightly different scale because of the object that we had in there before. So rescaling as it is by just material type along here gives us this kind of model, which is not a bad representation. But if I change this to look at, say, the marrow, you'll see that some of the edges here are quite hard. So actually, some of what we've called marrow here is probably bone. It's always going to be hard to try and choose those thresholds very easily. If I just click air as well, that's actually quite a nice representation of what's inside the bone. I think there wasn't actually much in the way of what was above. I think there are some very tiny dots in the middle there, that a couple of voxels that were actually higher than 180. But this is a pretty good illustration of what our intensity mapping is doing, and it has actually picked out what I would think is bone pretty well. If I go back now to look at the output files, what the intensity mapping actually did was create a whole new group file for us, and then it loaded that instead, and it decided that going with our 4 groups, that there was a group 1 to 1 for marrow, 2 to 2 for air, and then 3 to 35 for bone. So it created all these divisions for our bone, almost as we asked. Probably if we'd adjusted that approximate divisions a bit higher, it might have increased that for us. But generally, that would probably be enough anyway to use in our finite element model. And then the last group was 36 to 36, and only bone here has this capability of being remodeled, which would more or less be the default in any kind of normal situation. And if we have a look at the materials file that got generated from that, then we should see that reflects these groups. So 1 was this marrow material that we declared, 2 is this very low modulus air material, and then we have all these intermediate levels for the bone, which you would need to adjust according to any given problem. And then there's this last group, which we set for very high voxels. So I hope that explains in some useful way what happens between groups and blocks and materials in VOX-FE. Thank you.